Guys, it's very late, but I was after to show that pi is irrational, so I grabbed the 2003 paper that's there, and I gave it a whirl. So bear with me because this is a long one. Can take me ages to upload, but that's okay. So we started with this one here. Okay. Look, it gave you the best bit. Now this is worth 3 marks, 3 very achievable marks here. And it told you that you had to use by parts twice. So the obvious one here is splitting up the cos function and that, and obviously you can't integrate that. So that will be u, differentiates this, cos goes to sine, pretty simple stuff. Then you get uv, which conveniently goes to 0, given those limits. That section there goes to 0. And then you end up with that. Now that did not look great, and I must admit I thought I was doing that wrong, except that... There we go. Except that it turns out, when you get to this bit here, you take the n out as a common factor, or as a constant rather. That cancels with the n factorial to give you the n minus 1 factorial. That's awesome. We also had a 2 there, so took that out the front. Then you're left with this. Now, if I'm going to do by parts, it's pretty much going to be the trig function again. And this bit, but that's okay. I can differentiate that and do that. The product rule, which is what I did there. I'm going to add photos of all of these, so if this is going a bit quick, don't be too worried. You can have a look at the photos. So, when I do the product rule and the by parts, this is what I get there. Now, that goes to 0 again, yay. And then we get this bad boy here. Now, conveniently, it does come in the 2 parts, the in minus 1 and the in minus 2, which is good. Then we get down to this bit here, that's perfect. And then you get this constant out the front here, which is actually really good, because the n minus 1 will cancel, right here, there we go. The n minus 1 and the n minus 1 factorial will cancel, to actually give you very close to what you want. I think that might actually be what you want there. Yeah, so... yeah, and then the next step is just what it asked for, which is awesome. So, part 2 was a little bit trickier because it wanted in minus 1 and in minus 2. Now, I went down a very bad track where I swapped that one there for in minus 1 straight away. That's bad because obviously that is not in minus 1. In minus 1 must include the constants out the front. It was q to the 2n, so that now must be q to the 2n minus 1. And of course it was n factorial on the bottom, but now there has to be n minus 1 factorial. So this whole thing has to be in minus 1. So it was actually quite a job to get there. I broke it up into 2 parts. So I did that part first, that's the green part. And then I did that part there, which is the purple part. The purple part was obviously a little bit longer. So I changed this constant out the front to what I wanted by taking the 2 out and then a q squared out. Gave me exactly what I wanted, which is awesome. The purple part is the bit where they need to use that hint. So I used that hint there to break this up. Then I expanded it. So I expanded by that and then by that. Now, side note. In minus 2. What does it need to look like? It needs to look like this. So it needs to be q to the power of 2n minus 4, n minus 2 factorial, and all of that. And so I made that. Yay! That was not too bad. And... yeah, I made that. That's awesome. That's what I wanted, so that's okay. Then I expanded that here, still got that little cos x there, which is good. And then we get down to this bit. Now, that is just a constant that I can pull out the front, and there's in minus 2. So that's awesome. Pi squared on 4 there. This was a problem, though, because I got in minus 1 again, but I don't have the right constant out the front. So I need to fix that up. Now, I'm pretty sure... yes. I got to this bit. So I've taken the constant out the front there, and then that's perfectly in minus 2. Okay, so that's just the constant that we had before. And then the other part of it is this part. Now this constant here is wrong. It needs to be in minus 1's constant to match the power. So I did some fanciness, and here is that fanciness. It follows down here that basically I need an extra q squared on top. So I'm going to multiply by q squared over q squared, obviously, because I can't just multiply by something. I need to multiply by 1. And the n minus 2 actually need to be n minus 1 factorial, so I'm going to have to multiply it by n minus 1. When I do that, I get the constant that I want, but I have this extra things. Q squareds cancel here, and I end up with this. And the constant I want. Yay. So that's how I did that. And then we get down to here, and the purple part actually gives us this. I made a negative error there, so watch out for that if you were doing it at home. And it gives you this long thing here, collect the like terms there. Oi, pi, that's p on q, I remember that from the start. And so I substituted that in, and bang, phenomenal. That was worth 1 mark. Gentlemen, that's a toughie. So part 4 was a bit interesting. Explain why, part 3 rather, explain why it must be an integer. Look, I'll take a photo of that again, but basically, it said that I0 and I1, so that should be I2, that one there. Please ignore the 3, it should be I2. Basically, if you combine integers in the way that they are combined, 4n minus 2 here is always positive and can't be a fraction, that can't be a fraction, that can't be a fraction, this can't be a fraction. There's no part of it, there is no combination that will give you anything but another integer. And that's basically what I said, that there is no way to combine the p's, the q's, and the n's that are part of in minus 1, that's part of in rather, to give you anything but an integer. And so I2 will be an integer, and therefore if I2 is an integer, I3 will be an integer, and so on and so forth. They're basically looking for you to say that if I0 and I1 are integers, then I2 must be an integer, and then so on and so forth. And then we get to this bit. Now part 4, honest to God, took me half hour, 45 minutes. This was a tough one. So basically it said, okay, an inequality. Now inequality integrals, remember that this is a definite integral. So a definite integral is going to have a area. It's going to produce an area. And so if we can find a comparable area that is always bigger, then we can say that integral must be bigger. And that's exactly what I've done here. So this function was being multiplied by cos x. Now between 0 and pi on 2, in fact, for any values of x, that's going to be less than 1. And so if I multiply the height of this function by something that is less than 1, so this bit by something that is less than 1, then I'm obviously going to reduce the height and thus reduce the area. And so this area must be smaller than this area because I'm no longer multiplying by the cos. Now that's a fairly steep jump, but not like in terms of really difficult questions. I have seen that before. So I thought, hey, that's amazing. And then obviously I wasn't done here because this is really very similar to this, except that I always minus x squared. And because x must be between these two values and I square it, that value there is always less than that value there. So again, you take a height that is pi squared on 4 and you are constantly taking something away from it, which means that that must be always less than the this, just pi squared on 4. And so because I can say that the areas must be bigger, then this must be bigger than that, which therefore must be bigger than that. It's a bit like our 3 people in a row. If he is taller than him and he is taller than him, then he must be taller than him. Same deal here. Now that's, again, a rough step. Keep in mind this is 2 of the last marks on this paper. Fortunately, once you do that though, it's pretty straightforward from there. Integrating that's pretty simple because it's just a constant. You do some fanciness with pi here, take p on q out, replace pi with p on q, and look, it sort of settles out there. It should also be noted that this function, the original function, this one, because it's between these values, cos will be positive, this will be positive, therefore the whole function is above the x-axis, and so that when you integrate it above the x-axis, obviously you get a positive area, so the integral there must be greater than 0, hence that whole thing. Really, that's a tough 2 marks. Well, look, let's just finish it there. It's a tough 2 marks. The last mark is actually really easy. You get to this bit here, and it says, well, that's less than 1. You're like, well, okay, cool. That means that if that's less than 1, but that is bigger than that, then in must be between these two values. But if iron is between those two values, then part 3 is wrong, because part 3 said show that iron must be an integer. Now remember, one of the things we said was that iron must be an integer because there's no way to combine the 3 unknowns that are integers into anything but an integer. In other words, N, P and Q were combined in a way that if they were integers, you could only get an integer. Which means one of them can't be an integer. But of course N has to be, because it was defined as an integer. Which means P or Q must not be an integer, one of them at least. And then that means that pi must be irrational, because it cannot be expressed as a fraction P over Q where P and Q are integers. At least one of them is not. And then you've finished. Look, that's a tough question. I really actually enjoyed it, as you can tell by the lateness at which I am posting this video. But anyway, that's a tough question. Keep studying. Bye.